Hello and welcome to this Nikon Metrology Clemex webinar. My name is Renat van Kouter. I'm responsible for marketing at Nikon Metrology. I will introduce this webinar, which will last about 25 minutes. Today's topic discusses automated steel inclusion rating systems based on Clemex technology and Nikon microscopes. We will cover system components, applications and benefits of the combined solution. First, I will provide a short introduction on Nikon Metrology. The Nikon Group was founded in 1917, so this year we are celebrating our 100th birthday. Today we have some 25,000 employees worldwide. Nikon Metrology is established in 2009 and headquartered in Leuven, Belgium. The Nikon Group comprises of 4 principal business units, all with a common theme: solutions and products centered on optical technology. This is our expertise. The imaging products are very famous and include cameras, lenses, binoculars, etc. Nikon Metrology is part of the industrial metrology division that comprises optical measuring solutions such as computed tomography systems, laser scanners for CMMs and articulated arms, large volume measuring systems, video measuring systems, industrial microscopes and software. Other important business units are the semiconductor systems and the recently established healthcare division, which includes the biological microscopes. For the industrial microscopy line, Nikon Metrology holds strategic partnerships for specific applications, peripherals and accessories. Today's presentation focuses on the application of material testing in cooperation with Clemex. Let me introduce you Mr. Raymond Tadza, Application Specialist at Clemex Technologies, who will further host the webinar.
Thank you, Renat, for having us today on this webinar. I am Raymond, and I will be introducing you today to Clemex CIR. Clemex was founded 25 years ago, and we are the creators of the Clemex Vision PE image analysis software. We specialize in image analysis through microscopy, and we are also the integrators of hardware and software image analysis for your image analysis needs. Clemex is present in many industries. Some of those industries include automotive, manufacturing, universities, and research centers. And some applications that we are involved in are coating characterization, micro-hardness testing, non-metallic inclusion rating in steel, which we will be looking at today, and finally, grain size evaluation. Keep in mind that those are not the only applications that we do. The full Clemex product line is divided into 2 products. The first part is the multi-purpose image analysis line, and the second part is the specific image analysis line. The specific image analysis line, we have 3 popular products. The first one is the Clemex PS filter system, which is used for contaminants analysis on filters. Here we have metallic and non-metallic particles on a mesh filter. Next, we have the Clemex CMT system, which is used for micro and macro hardness testing. And finally, Clemex CIR, which we will be discussing today. Here we have a Nikon Vision, a Nikon MA200 with a auto stage, a camera, and then the CIR software. Here we have an alumina inclusion in steel. Next is the multi-purpose image analysis product line. First is the Clemex Vision Lite, which is used for simple and single applications. Here we have a quoting layer, which we can analyze in 2 parts. The first quoting here, and the second quoting here. And the Clemex Vision PE system. This is our flagship software and is used widely for custom and complex image analysis routines in materials. Here we have a grain size for ferrite and pearlite. and we integrate Vision PE with an upright microscope. Here we have an LV100 camera and auto stage again. So what is automated inclusion rating? To explain to you what is automated inclusion rating, I will tell you about manual inclusion rating and how an operator uses this method to find inclusions. So first thing, an operator places his sample under a microscope. He analyzes a field, and then while analyzing the field, he must characterize and measure each inclusion. Once he's done, he must go on the next field, and he must do that until he reaches a required area. So for ASTM E45 method D, he would need to reach 160 square millimeter, which represents over 225 fields. An excellent operator would take about 30 minutes or more. So CIR's advantage is that it can automate all that quite fast, can take 2 minutes per sample for 160 square millimeter sample for ASTM E45. It has automatic edge detection, so the operator doesn't need to set his pattern precisely right away. He can just find where his sample is and click go, and it's repeatable. So CIR can repeat the same task over and over again and will always generate the same results, but an operator may not do the same. So we will be looking today at two types of standards. We have the ASTM E45 standards and the ISO 4967 standard. The ASTM E45 standard has 4 types of inclusions. There's the sulfide, the alumina, the silicate, and the globular. And ISO has the same plus the globular DS inclusion. Before we start the Clemex CIR system, we need to place polished sample in a sample holder. We will now look at the first video, which will demonstrate one sample run on ASTM E45. So what we're doing here is we're going to be doing basic thresholding for oxides and sulfides. So by doing so, we will be characterizing the sulfides, which are lighter in color, and the oxides, which are darker. And after we characterize that, the software will then be able to divide the oxides into 3 more inclusions. It will be silicates, which are smooth in shape, aluminas, which are rougher, and globulars, which are round. So now we activate the basic thresholding. Here we edit the number of heats and samples that we have. In this case, it will be only 1 sample and 1 heat. Once we're done, we set our pattern. Here what we see is where we are on our sample. So this rectangle represents our field of view currently that will be shown in the image window here.
Now the operator is looking for the best place to start his pattern on the sample. We typically look at the edge and be close to it. Once we're done, we move it and set it, and our inclusions were horizontal. Here our pattern is set at 170 square millimeter.
But here, as you can see, we can recreate the pattern according to a standard, which is 160 square millimeter for ASTM E45. And we also activate our linear focus, which we will see later. So we have a choice of 3 standards pretty easily through a drop-down menu. And once we're done, we can click Start. So what the software is doing here is finding the edges of our sample. This is when we talked about the fast edge detect. By doing so, it will detect all of the sample and recreate the pattern according to the standard. In this case, it's 160 square millimeter. You may wonder why here we have a small line that's moving and the rest of the image is frozen. This is because we're only detecting the edge right now, and we only need part of the image to be processed, which saves a lot of time on computer specifications. So now we're detecting the third edge and the fourth. So what we're going to be doing now is the linear focus. The point of the linear focus is that it will find 3 points that are far away from each other and focus on those 3 points. And once it finds the focus points on those 3 areas, it will create a focus curve, which will be in focus on all of the fields. So we save a lot of time doing so instead of focusing on each field by setting a plane with 3 points. So we're done. The pattern is green on the right, and we're already starting the analysis. What it's doing now is detecting everything that it's seeing on the sample, and once it's done, it will filter out anything that is not an inclusion and will keep the inclusions. So now we're about done with the analysis. It's compiling everything that it found. And here we have a map. The next video, we will be looking at the map and validating the results that we just generated. So what we're doing now here, we're filtering out the inclusions that we found so that an operator can look at the worst fields for one inclusion. Here, we're only active right now on the sulfide. And what you can see here on the image window became a map of our whole sample. We have a thick square here, which represents the ASTM E45 field of view. And here we have a thin one. So the thick one represents the heavy inclusions, and the thin one represents the thin inclusions. You can notice here that this floating window is over 4 fields of view of the camera. So this is the big advantage with CIR, is that we're not limited to the field of view of the camera, but we create a map and we can reconnect the inclusions and find any heavy inclusion no matter where they are. So we're going to be looking at that thin inclusion here. As we can see, we have a scratch on the bottom, and it was detected as an inclusion. The reason why it was detected as an inclusion is because it was on the same orientation that we chose, horizontal. You can notice here that this one was not detected because it's not in the same orientation. So this is part of the work that an operator must do. He must clean his sample. And once it's clean, as you saw, this thin inclusion worst field floating window was here, and it moved here. So it always goes on the worst field. I'm going to be looking now at the heavy inclusion. We're going to deactivate our threshold, and those seem good. When I look at our thin inclusions for sulfides, this also seems good. Next is alumina. This is the thin inclusion. This is also good, has a rough shape. And our heavy inclusion, also good. I'm going to look at silicate. We have no silicate on this sample. Finally, globulars. They need to be round in shape, so this isn't good, neither is that. So the operator here has access to all of the methods from ASTM. He doesn't need to run the sample again and again for each method. He gets them all right away at a click of a button. And we have also access to the oversize. Here we see that we have two oversizes in alumina. We're going to take a look at them. On the bottom here, I'm going to look at it. This is dirt. There is another one. I'm going to look at it. You're going to notice that this was detected because of its rough shape. As I told you, alumina has a characteristic to be a rough shaped inclusion, but the operator knows that this is not an alumina inclusion. This is actually bad preparation. The results here got updated on the fly. As you had noticed, maybe we had two alumina inclusions. They aren't here anymore. So as the operator goes, the results get updated. Once the operator is done, he can choose a method, choose to export it as a report. He can select one or all of them and export it on Excel. Now we're going to be looking at multiple samples using the ISO 4967 standard. As you can see on the right here, we have 30 samples. We have 5 heats, and each heat has 6 samples. So we can handle quite a lot of samples with CIR. It's not only one sample that we can analyze up to 30 samples, as you can see here. So what we're doing now here is we're showing you the location of each heat. As we click, it changes. The name also changes on the bottom. So we click on one. The sample is here. And we're going to be analyzing only one heat in this case. So we chose one heat, and we'll be analyzing all those samples. So we're not obligated to analyze all of our patterns. We can only choose one heat and a few of the samples from that heat if we choose to. So once we're ready, we're going to notice here that it's set at 200 square millimeter, but here it's 160 because the standard is not chosen. We're going to be choosing here ISO standard, which is 200 square millimeter. You notice that it just changed the recreate pattern. In this case here, we'll be using loaded images instead of a live sample. We'll only be analyzing one heat and 6 samples. So it's the same process as before. We're almost done with our first sample. We're going to be moving now to our second sample. That's our second sample. It does that until we reach our final sample. We're on the 6th sample now. So here we have the results for all of our samples. As you can see in this window, we have the different methods for the ISO standard. We have method A, B for total number of fields, and also B for global cleanliness index. So we get the average per sample and also the average for the whole heat on the bottom. Here it's for the total number of heats. This is very close to the JK chart standard that you have, an operator might have in his room. So as we change samples here, we're going to be clicking on a different sample. We're going to see that the map is going to change. So that's what we're talking. That's the advantage of having a map and doing multiple samples at a time. An operator can do them all and clean them after the operation is done. So that saves a lot of time. So we're we're looking at an alumina inclusion. We only have a thin one here. Silicates, there aren't any. Let's look at DS. It has a round shape, so this is fine. Let's look at sulfides. Once we're done, we can export the report again. You can choose one method or all methods. And we can rename it as well. And that's pretty much it. Let's take a look at our many sample holders that we have. So the first one is for mounted samples. The second and third one are for unmounted samples. The advantage of using unmounted samples is that you don't need to mount your samples. A mounting process can take at least 10 minutes. So imagine mounting all of that, you're wasting 60 minutes at least. And also, as you can see here, we have magnets. The advantage of the magnets is that we can place our sample on the sample holder, and it's going to go on the corner automatically because of the magnet. That way, when we use the pattern tool in CIR, you won't need to move it that much. But with a mounted sample, you never know what you're going to get. So you're going to waste more time using the pattern creation tool. Also, with unmounted samples, we can fit more samples on one sample holder. Here we can fit 12, we can fit 18, and depending on the size of your auto stage, we can fit even more. This is a workplace window that we saw in the video. So the first part here is the list of heats and samples. Here is the stage travel area where we create our pattern for each sample that we have. Those are the X, Y, Z coordinates on our auto stage. And here we can choose to recreate a pattern using a standard and activate the linear focus to be in focus throughout the whole sample. Once our run is done, we get a results map. Here we see a results map with heavy inclusions and with different inclusions, with alumina, which is here, sulfides, globulars, and silicates. So the advantage of using an automated inclusion rating system and the Clemex CIR system is that we comply with many standards. As we saw, we just looked at ASTM and ISO. We have fast analysis, so it takes less than 3 minutes for an ISO standard to be analyzed. This is 200 square millimeter. We get consistent and accurate results because of the precision of an auto stage and our software, which in turn reduces the interpretation of data. An operator can interpret data from one to another. You can get different data. That's not the case for CIR. We get integrated systems. So Nikon and Clemex can sell you a system like that. Here we have a Nikon MA200 with an auto stage, a camera, and the software. All of that, you can get it from either Clemex or Nikon. We can create custom sample holders. So if you don't have standard shaped samples, we can create a sample holder for that. We have a machine shop here. And easy reporting. So once you're done with your analysis, we can export that on Excel. Let's start our question and answers time.
Thank you, Raymond, for your explanation. There are a few Q&A questions already that came in. Can you hear me, Raymond?
I hear you.
Yes, okay. So a first question that I received is, must the sample be perfectly polished?
So yeah, that's a question that we get often from our customers. The better the polish of a sample, the less work at the end. So as you saw on our video, we had a scratch on our sample. That's because of preparation. And this was a pretty good preparation for a sample. So imagining that we have even worse preparation will result in more manipulation of the data once we are on our map. So that will consume some time on the operator per sample. So what we usually tell our customers is have a good polish that will result in less work at the end. And it's also good practice to have a perfectly polished, well, almost perfectly polished sample.
Okay, thank you. Another question that we have is, our samples are flat metal sheets. How do you handle that?
Okay, so if you have a flat metal sheet, what we typically tell our clients is to stack them together in a mount, and then while they're in this mount, to polish them. Once you polish them, we have an option in our software, which I have here. Is for multi-steel plate samples. So what it will do is, because there's an interface line between each metal sheet, it creates lines, and we don't want the software to count that as an inclusion. So what we tell it is, if the length of an inclusion is greater than 98%, then it will be removed. So all of the interface lines will then be removed with this active.
Okay, thank you. A third question I received was, we don't have silicate in our steel. How will your system handle this?
So if you don't have silicate in your steel, as in our sample that we just ran today, what we have is also another option where we tell,
It's something in the INI file.
Oh, it's somewhere else. It's not present in there, but once we do the installation, we can go in the configuration file and set an option where any silicate that it may find will be classified as a sulfide. So because they're the same in shape, it's only in thresholding that they're not the same, that if it finds something that's in the same shape, it will automatically classify as a sulfide.
Thank you. Another question is, what other standards do you do?
So the standards, as we saw today, was ASTM E45, ISO 48967. We saw the options for GIS G0555 and DIN 50602. We also do ASTM E2283, which is the extreme value inclusion. That's used to find the largest potential inclusion calculated using statistics, when we also use the EN10247. In this case, you need a color camera, and it's for the worst field section.
And currently, the final question I received was, how do you differentiate your inclusion types?
So inclusions, as we saw before, are differentiated using basic thresholding. So with oxide and sulfide, those are the two main inclusions classification that we have. As we saw, the sulfides are lighter and the oxides are darker. And then oxides are divided into three other inclusions. For in the case of ASTM, we have alumina, silicate, and globular. And those are divided by their shape. So alumina are rough, silicates are smooth, and globulars are round.
Okay, thank you. There's one final question that arrived. Do we need to validate each sample? For example, when we are analyzing 30 samples, do we need to validate each one?
Yes, it would be normal to check them out, but normally, if the sample prep is good, you would take about 15 to 30 seconds per sample to validate it, because you need to check all the inclusions, not all the inclusions, but all the worst field. Once you have the worst field correct and the polishing is good, normally 1 or 2 steps at worst, and then it's a typical procedure that doesn't take a lot of time. So the cleaner the sample, the less work there is. But like everything else, having a good preparation is as important as having a good dimension on a tensile testing or a chemical analysis. You would put the right constituent in there. So in this case, you need to have a good sample preparation, and it's pretty easy to adapt to a good procedure.
Okay, thank you. Currently, there are no further questions, so I suggest that we end this webinar. So thank you all for being here. We will also have a recording that we will distribute to everyone that attended, so you can eventually review or re-listen to the webinar. So therefore, thank you again, and see you next time.
Thank you. Thank you.